Energy is a very important concept in physics and science in general. It is the ability to do work or heat objects. Work is the transfer of energy by a force that causes an object to move. Heat is the transfer of energy by a difference in temperature. Energy can exist in many different forms, such as kinetic, potential, thermal, electrical, chemical, nuclear, and others. Each form of energy can be converted to another form, but the total amount of energy in a closed system remains constant. This is known as the conservation of energy principle 1. Kinetic energy is the energy of motion. It depends on the mass and speed of the object. For example, a moving car, a flying bird, and a spinning top all have kinetic energy. Potential energy is the energy of position or configuration. It depends on the height, shape, or state of the object. For example, a book on a shelf, a stretched rubber band, and a compressed spring wall have potential energy. Thermal energy is the energy of heat. It depends on the temperature and amount of matter. For example, a cup of hot coffee, a burning candle, and a radiator all have thermal energy. Electrical energy is the energy of electric charges. It depends on the voltage and current of the electric circuit. For example, a battery, a light bulb, and a lightning bolt all have electrical energy. Chemical energy is the energy of chemical bonds. It depends on the type and amount of molecules. For example, a piece of coal, a candy bar, and a stick of dynamite all have chemical energy. Nuclear energy is the energy of atomic nuclei. It depends on the mass and type of atoms. For example, a uranium atom, a hydrogen atom, and a sun all have nuclear energy. Energy can be transferred from one object to another, or from one form to another, by various processes. For example, when you lift a book, you transfer some of your chemical energy to the book as potential energy. When you drop the book, the potential energy of the book is converted to kinetic energy as it falls. When the book hits the ground, some of the kinetic energy is transferred to the ground as heat and sound. The total energy of the book, the ground, and the air remains the same before and after the process, but the distribution of energy among them changes. Energy is measured in units of joules, J, where 1 J equals 1 kgm 2. Other units of energy include kilowatt hour, kWh, British thermal unit, BTU, calorie copyright, kilocalorie copyright, electron volt, EV, erg, and foot-pound, FTLB. Different units are used for different purposes and contexts. For example, kWh is used for measuring electricity consumption, BTU was used for measuring heating and cooling efficiency, calorie is used for measuring food energy, and EV is used for measuring atomic and subatomic energy. Energy is a fundamental concept in science and engineering, as well as in everyday life. It is essential for understanding how things work and how to use them efficiently and sustainably. Energy is also related to other important concepts, such as power, force, momentum, and entropy. By learning more about energy, you can gain a deeper insight into the natural phenomena and human activities that shape our world. The amount of energy in a system depends on the type and form of energy that the system possesses. There are many formulas for energy, but the most general one is the first law of thermodynamics, which states that the change in internal energy of a system equals the heat added to the system minus the work done by the system 1. In symbols, this is U equals QW, where U is the change in internal energy, Q is the heat, and W is the work. All these quantities are measured in joules, J. To calculate the amount of energy in a system, you need to know the initial and final internal energies of the system, as well as the heat and work involved in the process. The internal energy of a system is the sum of the kinetic and potential energies of all the particles in the system. It depends on the temperature, pressure, volume, and composition of the system. The heat and work are the ways that energy can be transferred between the system and the surroundings. Heat is the transfer of energy due to a temperature difference, and work is the transfer of energy due to a force acting through a distance. For example, suppose you have a gas in a cylinder with a movable piston. The gas is an initial internal energy of it, and you compress it by applying a constant force F to the piston, reducing its volume from V to the F. The gas does work on the piston, and its internal energy decreases. The work done by the gas is equal to the force times the distance, which is also equal to the pressure times the change in volume. The final internal energy of the gas is UF. The heat transferred between the gas and the surroundings is Q. The change in internal energy of the gas is U equals UF equals QPV, where P is the pressure of the gas, and V is the change in volume. If you know the values of width, q, and p, you can calculate the amount of energy in a system using this formula. Energy is a very important concept in quantum mechanics, as it determines the behavior and properties of subatomic particles and systems. Energy is quantified, meaning that it can only take discrete values, not continuous ones. This is different from classical mechanics, where energy can vary smoothly and continuously. The quantization of energy is a consequence of the wave-particle duality of matter and radiation, which states that both can behave as waves or particles depending on the situation. As waves, they have a wavelength and a frequency, which are related by the equation F equals c, where is the wavelength, F is the frequency, and c is the speed of light. As particles, they have a momentum and an energy, which are related by the equation P equals h, E equals hf, where P is the momentum, E is the energy, and h is the Planck constant, a very small number that sets the scale of quantum phenomena. These equations show that the energy and momentum of a particle are proportional to the frequency and inverse wavelength of the corresponding wave, respectively. The quantization of energy arises when a particle or a system is confined to a certain region of space, such as an atom, a molecule, or a box. In this case, the wave function of the particle or system, which describes its probability of being in a certain state, must satisfy certain boundary conditions. These conditions restrict the possible values of the wavelength and frequency of the wave function, and thus the energy and momentum of the particle or system. For example, in the case of an electron in an atom, the wave function must be zero at infinity, and must match the electric potential of the nucleus. This leads to the famous Bohr model of the atom, where the electron can only orbit the nucleus at certain distances, corresponding to certain energy levels. The energy levels are labeled by a quantum number n, and are given by the formula n equals n2r, where r is the Rydberg constant, another small number that depends on the mass and charge of the electron in the nucleus. The energy levels are negative because the electron is bound to the nucleus by the electric force, and the lowest energy level, n equals 1, is called the ground state. The electron can jump from one energy level to another by absorbing or emitting a photon, a quantum of light, whose energy is equal to the difference between the two levels. This explains the origin of the atomic spectra, the characteristic frequencies of light emitted or absorbed by atoms. The role of energy in quantum mechanics is to determine the possible states and transitions of a quantum system, as well as its interactions with other systems. Energy is also related to other physical quantities, such as angular momentum, spin, and magnetic moment, which are also quantities in quantum mechanics. Energy is also conserved in quantum mechanics, meaning that the total energy of a closed system remains constant, although it can be redistributed among its components. However, energy conservation can be violated in very short time intervals, due to the uncertainty principle, which states that there is a trade-off between the precision of measuring the energy and the time of the measurement. This allows for the creation of virtual particles, which are temporary fluctuations of energy that can affect the behavior of real particles. This is the basis of quantum field theory, which describes the interactions of particles and fields in terms of energy exchange. Energy is related to space-time and general relativity in several ways. Here is a brief overview of some of the main concepts. Special relativity explains the relationship between space, time, mass, and energy. It shows that space and time are not absolute, but relative to the observer and the speed of the object. It also shows that mass and energy are equivalent, according to the famous equation E equals 2, where E is energy, m is mass, and c is the speed of light. One general relativity describes how gravity fits into the mix. It shows that gravity is not a force, but a consequence of the curvature of space-time caused by the presence of mass and energy. The more mass and energy an object has, the more it bends the space-time around it. This bending affects the motion of other objects in the passage of time. Einstein field equations are the mathematical expressions of general relativity. They relate the geometry of space-time, expressed by the Einstein tensor, with the distribution of mass and energy within it, expressed by the stress-energy tensor. They are a system of nonlinear partial differential equations that determine the metric tensor of space-time for a given arrangement of mass and energy. The metric tensor describes the properties of space-time at each point, such as its curvature, length, and angle. Two spacetime diagrams are useful tools to visualize and understand relativistic effects, such as how different observers perceive where and when events occur. They are graphs that plot the position and time coordinates of events in a given reference frame. The slope of a line on a spacetime diagram represents the speed of an object or a light signal. The shape of the spacetime diagram depends on the choice of reference frame and the curvature of spacetime. Einstein's field equations are a set of 10 equations that describe how gravity works in the context of general relativity. They show that gravity is not a force, but a consequence of the curvature of space-time caused by the presence in motion of mass and energy. Here is a detailed explanation of the equations and their meaning. The equations can be written in the form G equals C48gt, where G is the Einstein tensor, T is the stress energy tensor, G is the gravitational constant, and C is the speed of light. The Einstein tensor G is a mathematical object that measures the curvature of space-time at each point. It is constructed from the metric tensor G, which describes the properties of space-time, such as its length, angle, and shape. The Einstein tensor is related to another object called the Ricci tensor R, which is a simpler measure of curvature, by the equation G equals R21GR, where R is the scalar curvature, which is the average of the Ricci tensor over all directions. The stress energy tensor T is a mathematical object that represents the distribution of mass, energy, momentum, and pressure within space-time. It is defined by the equation T equals G2GSM, where Sm is the action of the matter fields, which is a quantity that describes the dynamics of the matter, and G is the determinant of the metric tensor. The stress energy tensor is a symmetric tensor, which means that T equals T for any indices in one. The equation G equals C48gt expresses the fundamental principle of general relativity, which is that the curvature of space-time is proportional to the content of mass and energy within it. The constant of proportionality is determined by the gravitational constant G and the speed of light c. The equation is a tensor equation, which means that it holds in any coordinate system or reference frame. The equation has 10 components, corresponding to the possible values of the indices n, which can range from 0 to 3. However, not all of these components are independent, because the equation has to satisfy some consistency conditions, called the Bianchi identities, which reduce the number of independent equations to 6. These conditions also imply that the stress energy tensor is conserved, which means that the total amount of mass and energy in a closed system does not change. The equation is a nonlinear partial differential equation, which means that it is very difficult to solve in general. Only a few exact solutions are known, and they usually require some simplifying assumptions, such as symmetry or homogeneity. Some of the most important exact solutions are the Schwarzschild solution, which describes the gravitational field of a spherical mass, the Kerr solution, which describes the gravitational field of a rotating mass, and the Friedmann-Lemaitre-Robertson-Walker solution, which describes the expanding universe. The equation can also be solved approximately, by using various methods, such as the linearized approximation, which assumes that the deviations from flat spacetime are small, the post-Newtonian approximation, which assumes that the velocities are much smaller than the speed of light, and the perturbation theory, which assumes that the solution can be expanded in terms of small parameters. These methods are useful for studying phenomena such as gravitational waves, gravitational lensing, and the perihelion precession of Mercury. Have a nice day.